Okay. So I want to introduce the idea of E derivatives and E brackets in this class. And for the most part, this will require me to introduce the idea of integral curves. So we'll talk about the manifold. Yeah. And there's some curve gamma on M. I'm going to parameterize gamma by T. And I start at some point, say I start at which T is 0, and that's when my curve starts. Okay. And then we'll be talking about vector fields on these manifolds. So I can draw a vector field as well, just generally. And I want a very specific vector field to come into play. Let's draw arrows on this manifold corresponding to vector fields. There's one particular, given a particular vector field on the manifold, there's one particular curve that is special. Yeah. And this is the curve whose tangent vector at any point along the curve is that vector field evaluated at that point. So the vector field defines for me a curve. This curve is called the integral curve associated with that vector field. So given some vector field x, an integral curve of x is a curve whose tangent vector at the point x of t is x evaluated at x. Two, three, four, five, six, seven, 8. This is an integral curve of x, the curve with tangent vector. At x t is x evaluated at t. So keeping in mind the definition that we use of tangent vector, this means that in some chart given phi in which I associate coordinate x mu to the point xt, x mu satisfies a first order differential equation. T, let's say that the x mu by dc is x mu, capital X mu of s. So yeah, the x mu is the mu component of phi x of t in thought. And capital X mu is the mu component of x coordinate basis in the chart u phi, and x here is a specific point in M. So if I want to compute the integral curves associated to a particular vector field, I need to solve this differential equation. Subject to some boundary conditions, the boundary condition that we'll use is that the curve starts at point x1. First order differential equation, and the uniqueness and existence theorem in ODEs assures us that such a solution does exist, at least locally in this charge. So systems uniqueness theorem of these. Fusion exists. It's locally. So how I patch together solutions in different charts, not a problem, but as long as I stay within the particular chart, then I know that a solution will exist. Yeah.
I think does that have to hold at t equals 0 because the derivatives we like to find in quantity?
Does it have to hold that t equals 0? Yes, it does. I'm learning you guys' names, so let's
Sorry.
Okay. Very good. So yes, that's a obviously like does have to hold that t equals 0. So basically anything that I need for the first order ODE to make sense needs to hold here. And all the axioms that go into existence and uniqueness also needs to hold. So let me do an example to illustrate. So suppose x is x squared x plus y y on r squared, and that's gamma of t being parameterized by x of t, y of t. That's such. Then gamma of t will be an integral curve of this particular x, if and only if gamma prime. So gamma t is an integral curve of x, and only if gamma prime t, gamma by dt, is x, evaluated at gamma t, which means the following. If I differentiate, then I'll find that x prime, meaning dx by dt, dx plus y prime dy is equal to x evaluated there, which is x squared dx plus y dy. Two vectors, and they're equal if they're on one side equal. So this means I get a system of ordinary differential equations which said that dx by dt is x squared and dy by dt is y. So this is a just a system of what we can call then that x of t is 1 over let's say a over 1 minus a t, and y of t is e to the t, or e to the t, so let's say e to the t, where a and b are integrated constants. And these integration constants are the value of gamma of naught. These are the initial conditions on the curve. So you specify what the A's and B's are, and that will tell you what the specific solution of x of t and y of t are, and the combination pair x of t, y of t determine the curve, and that curve is an integral curve of this vector. Is that clear? So what this means is that if sigma of t x naught is an integral curve of some vector in x, then that passes through the point x naught in M at t equals naught, then coordinates sigma mu t x naught, then we require that the sigma value t is equal to x mu of sigma of t x naught with sigma mu of naught x naught equal to x naught. So that's the initial value problem that we need to solve whenever you want to compute integral curves. Okay. What you can see is that this guy sigma of t x naught actually defines the map from r plus m. It takes in some parameter value, that's a real number, and some point in the manifold, and it chucks back a point in the manifold. So the map sigma taking r plus m to m is called the vector flow of this flow associated to the vector field x. Or another way of putting it is to more close to what we want to think about this. flow generated by this. And the flow satisfies the composition rule. That if I stop up at some point, x naught, and slow to some other point, sigma of around the value s, flow to sigma of s x naught, and then I start at that point, flow to another point, sigma of t, sigma of s and x naught. Then this is the same as starting at x naught and flowing to sigma of t plus f and x naught. So it's closed on the composition. Both sides of this equation make sense if both sigma of t, sigma of s and x naught, and sigma of t plus f and x naught satisfy the same differential equation with the same initial conditions. You can show that that's the case. So an exercise, even for you guys. Mathematics table for a fixed value of the parameter t. A slope sigma of t and x is a diffeomorphism from M to F. For anybody else who cares, it's a differential homeomorphism. If that wasn't clear, a homeomorphism is a map that is that is continuous with continuous inverse, and then in addition it's differential and it's differential. The flow defines the differential manifold of itself. So for a fixed value of t sigma x is a morphism this indicating it's t parameter x. So under the following rules for sigma, one, so sigma T of sigma S of X is sigma T plus S of X. Again, this is composition. I start with point X and flow to a new point sigma S of X, and then from there flow to sigma T. That's the same as if I flow from X sigma T plus S. Okay. So basically, you really can. Well, mathematics section, flow and analysis, for example. Think of this as, for example, a velocity flow. So, the arrow will define for you the flow of some velocity field, like a river. And the statement is, if I start off at X naught and flow according to the water flow to some point S, and then sigma S, and then flow from there to sigma T. That's the same as if I just stay on course and flow to sigma. Okay. So it does not think of this as a velocity flow. Secondly, sigma naught, when the parameter value is naught, is this identity map. Thirdly, that if I flow in the negative parameter direction, then that's the inverse of G to -1. Under these rules, sigma T forms a commutative group called the one-parameter group of transformations that locally looks like the additive group R, but not necessarily globally. So one parameter group of transformations. This is a commutative group. That locally looks off. So that's the one parameter group of transformations. I now want to look at a particular set. I now want to look at a particular set of such transformations where the parameter is an infinitesimal parameter. So I'm just going to take the T to be epsilon, and epsilon, as we all know, is mathematics equals small. So I want to consider an infinitesimal flow sigma epsilon, and ask what happens to the point X that it starts off. Under an infinitesimal flow, sigma epsilon X in M to point sigma near epsilon of X. This is just the same as sigma mu of epsilon X in the notation that we use there. And this is the next mu where I start off with. Taylor is found small variable epsilon, that's d sigma mu by dt plus terms that are epsilon squared and Taylor is found. But this sigma mu satisfies the first order differential equation. So where I see d sigma mu by dt, that's the mu vector field. So this is x mu plus epsilon x mu of x plus terms order. Technically, what I mean here is tx at 0 plus. So again, if I start with the point x mu, and I flow to the point sigma epsilon of x, then those 2 points are related by x mu plus epsilon, a small number of times the mu component of the vector. Okay? Just because this guy here is satisfied with ODE. And I'm going to drop these terms in general because I'm going to assume that epsilon is small, epsilon is squared. I'm going to neglect. And in this context, especially because we will revisit this in the day when we talk about the algebras and the groups, this x mu is known as the infinitesimal generator of the slow sequence. Okay. We can turn this around, right? For a given set of components x mu, can I write down flow? And the answer is yes. And the flow is related to x mu by exponentiation. So basically, given a vector field x, I can find an associated flow of sigma t. Given a vector field x, given a vector field x, the associated flows flow sigma t sigma x is e to the tx x mu. So what I mean by differentiating. Keeping in mind that the vector field x is an operator. So when I write down the exponential, this is an operator. There's derivative sitting in here, and I define this by Taylor expansion. In case you're not sure what that means. Goes. Okay. So now suppose I have two flows. So to a particular flow, I associate a vector field. So I have two vector fields that they x and y that live in n instead of vector field in n. And they each generate a flow. So x generates sigma, y generates alpha. The question I would like to ask is, how does y, which generates tau, flow along sigma? Is that question clear? I have two flows associated with two vector fields generated by two vector fields. I'm asking how one vector field flows along the flow generated by the other one. So suppose that sigma of S x and tau of T x are generated by x and y respectively. So that we need here is that d sigma mu by ds is x mu of sigma of x sx and d tau mu by y mu of tau dx, subject to their initial conditions. The question we want to ask is, how does y flow along? Let's draw a picture. Well, okay. So here's my manifold. And I start off at some point x. And the sigma x flows at some point sigma. Let's assume that we're talking about a decimal transformation here. So sigma epsilon of x. Okay. That breaks right there. So x also flows under tau to the point tau of let's say Tm x. And this is the flow. This is flow tau. So this is the vector y at x. This is the vector y at x prime is sigma epsilon of x. I want to know how this vector y flows from here to here. Now, the obvious thing that you would think of doing, maybe not so obvious because I keep hopping on the stack, is to take the difference between sigma of x prime, sorry, y evaluated at x prime minus y evaluated at x. Why is that wrong? They live in two different vector spaces. This lives in tangent theta. This lives in y at x, lives in tx on that, and y at sigma epsilon of x lives in tangent space T sigma epsilon of x. So they live in two different tangent spaces. So I can't directly take the difference like that. Okay. What I can do, on the other hand, is take something from this vector space to that vector space. Do I know of any operator that will do that? Anyway. Push forward. Okay. The push forward is a map that takes us from tangent spaces to tangent spaces. Okay. So to overcome this issue that we're having with pairing vector spaces, we need to push forward. So to compare y at x and y at x prime, we can use the push forward map sigma minus epsilon star that takes us between T sigma epsilon of x on M T x. And then take the difference. So then we'll be comparing two vectors that live in the same vector space. Okay, so instead of comparing this guy to this guy, what we have to compare is this guy to the vector y. The vector sigma minus epsilon star of y at sigma epsilon y. These two guys live in the same vector space, so we can define their difference in a sensible way. In particular, that difference defines for us a derivative operation. And that derivative operation is what happens when we take these 2 points and make them infinitesimally close to each other in a limit where the difference absolutely close to 0. But this defines for us the Lie derivative known by curly L of y along the slope generated by x. I'm just going to call it the derivative of y with respect to the vector x. And this is defined as the limit as epsilon goes to 0, 1 over epsilon times first of all, sigma minus epsilon star y and sigma epsilon x minus y x. And that is a sensible measure of how you compare vectors by the details. But here's the thing. This definition is every bit as impractical as the first principle definition of derivatives that we learned about the first year. Right? We learned it once, and you did one character building example of calculating it from first principle, and you forgot about it. For good reason. It's highly impractical. So let's see if we can give a more practical way of computing the mean derivative of y along x. Okay, so suppose I have some chart on M. And in this chart, write x as x mean, b mean, and y as y mean, d mean. This allows me to write down some importance in terms of order basis and vector space context in that chart. Then for infinitesimals, flow parameterized by epsilon. The point x mu flows to x mu prime, x mu prime, x mu plus epsilon x mu or x. And again, I'm dropping high order steps. So this is the same thing. They're expanding nearby with point x, and I can write x prime like this. Remember that it's flowing along the flow generated by the vector field x. So let's evaluate y at sigma epsilon of x. Y evaluated at sigma epsilon of x, and y mu of x mu prime, that's this side. And let me write E mu here, just because I need to evaluate it at x mu plus epsilon, and this will be defined as g mu exactly. But that's a formula basis for the technical space. At x epsilon x. So this is y evaluated at x plus epsilon times epsilon is a small number. So I can Taylor expand this. If I Taylor expand this, I'm going to get y mu at x mu plus epsilon x mu d mu y. Let's see. And mean all this is okay. At x plus epsilon x. Two first order in epsilon. Similarly, the push forward of this guy is sigma minus epsilon on sigma epsilon x. That's just all of this stuff. That's just all of this stuff. Y mu plus epsilon x lambda d lambda y mu d mu of x mu minus going back to point x epsilon x mu E evaluated now as x. If you take the derivative of these things, that's just y mu plus epsilon x lambda e lambda y mu. The derivative of dx mu by dx mu is going to be comic delta mu mu. It's 1 when x mu and x mu are the same, and it's 0 otherwise. Minus epsilon d mu x mu x. So this just gives me y mu e mu at x plus epsilon in the first order epsilon. I get x mu d mu of y mu minus y mu d mu x y mu d mu of x mu e mu that's x plus terms are order epsilon squared that I'm going to throw away, and then I'm taking the difference between this guy and this guy, and this guy is expanded in these components will be y mu e mu x. So when I take the difference between these two, this will cancel this out, then I divide by epsilon. That will get divided out. And then I take the limit as epsilon goes to 0. So any term sitting here is going to be at least order epsilon. And if I take the limit as epsilon goes to 0, all these guys are going to get killed off. And so what we find in a concrete expression for the lead derivative of x y, and it is the difference x mu d mu y mu minus y mu d mu x mu in basis x. Okay. Let me finish this last statement. So this is already one there. Doesn't involve limits, doesn't involve all that. Just terminate this, right? I give you the vectors, means I give you the components in some chart. If you know the components in the chart, you take the derivatives and you work out the difference. And that'll give you the region. But I can write it down in an even more compressed form. And the more compressed form makes note of the following. Notice that the lead derivative of a vector field with regard to a vector field is another vector. Right? This guy is a vector. The question is, what are these components here in terms of the vector fields? Let me show you what they are. So, point to note is that this is a vector. So I solve it over two vectors x and y, and I produce another vector, the lead derivative of y with respect to x. It's not the only way that you can produce vectors from vectors. Another way, given that x is an operator, it involves derivatives, you might think, well, I can compose two vectors. What happens if I go x times y, right? Meaning x operator y. So given these x's and y's, if we calculate x, y. What I really mean here is x, y, and okay. I have to stick some test function because these are operators. So what is x, y acting on this test function? Well, x, y acting on the test function is x mu d mu operating on y mu d mu minus. This is a derivative, which means it operates, it obeys units. This is x mu b mu y mu d mu times my test function. So this is just some element of functions and plus x mu y mu second derivative. I'm going to write this. Okay. So here's the thing. The presence of this second derivative term here means that this guy is not going to transform like that. It's going to square it. So this spoils the vector property. And you can check this by making a coordinate transformation. You'll see that that's not checked. However, so what we've learned by this is that x, y is not a vector, right? Even if x and y are vectors, x, y is not a vector. However, y acting on x, acting on f, is going to give you something similar. Looking object, and it was the base x and y everywhere I see it. This is similarly not a vector, but mixed partial derivatives commute. So if I take the difference of these two guys, using the fact that I'm summing over the mu's of the news, and that d mu d mu is the same as d mu d mu, the second order terms are going to vanish, which means that this object x commutated y. Again, technically, I mean this thing acting on some test function is x mu t mu y mu minus y mu d mu x mu, all of which acts on this function. This d mu is sitting outside. This is just the coordinate basics for it. In other words, the lead derivative of y along flow generated by x is nothing but this commutator of these two vectors. This commutator is often known as the lead bracket. And it's another way of generating a vector dealing with vectors. Here's another, yet another reason I like this one better than the other one. I can go to the fixed number of boards and that's it. Work this out for like 6 years of the lecture. For a 1 hour lecture, I can fill up the whole thing and I don't have to erase it. All right, that's it. So just keeping data generated for the
But like even the manifolds are single.
And then it's still cost.
So that's explaining about the ring. But you have to be careful about the ring that you get from the parameters that don't flow to an infinite number. That is
Yeah.
that's what it is.
Have you got the videos? Have you got No, the point
But change.
That's a pretty. That's a no explanation.
I thought they were.
Yes, I know. So we bring the complicated.
Where is knowledge that any words? Yeah.
I don't know. What? As soon as the components come out, I check.
I thought that it's like, oh, let me sit them together in on the spot.
That's the thing. Because I think the point is. I don't know about it. I don't know.
I did that once in my recent time. What's on? I did this one for recent time. Oh, well, it doesn't matter. I actually said, oh, you like it? You don't like. What do you do the problem? Okay, what's the?
Okay, so it looks like for sure.
For sure, protest.
No, for sure. Apology is not in there on mine.
We cut that off. Yeah. The force is going.